Hello viewers, I am BSSP Rajashekhar, Assistant Professor of Mathematics, Government Degree College for Women, Nalgonda. In today's class, let us discuss about linear transformations. In this class, first we quickly recap the definition of vector space and subspace, and let us recall subspace theorem, which is useful in this class. Let us also recap the definition of null space and column space, which will be useful in this class again. Later we will move on to linear transformation and kernel of a linear transformation and range of a linear transformation. Later we prove that kernel of a linear transformation is a subspace of V and range of a linear transformation is a subspace of W, where T is the transformation from a vector space V to W. So this is the class map. First, let us quickly recall our definition of vector space. A vector space is a non-empty set V of objects called vectors on which two operations called vector addition and scalar multiplication are defined by the 10 axioms. Those are: for all u, v, w belongs to V and scalars c and d, first axiom is u plus v belongs to V. That is, V is closed under vector addition. U plus V is equal to V plus U. Commutative law holds with respect to vector addition. And U plus V plus W is equal to U plus V plus W. Associative law holds in V with respect to addition. And there is a zero vector O in V such that U plus O is equal to U. For each U in V, there is a vector minus U in V such that U plus minus U is equal to O, the zero vector. Here minus U is the negative of U. And scalar multiple of U by C is denoted by Cu. Then Cu must be in V. And C plus D times U is equal to Cu plus Du. And ninth one is C times Du is equal to Cd times U. And the last one is 1U is equal to U. If all the 10 axioms are satisfied by a non-empty set, then we call it as a vector space. A subspace of a vector space V is a subset H of V that has three properties. The zero vector of V is in H. H is closed under vector addition. And H is closed under multiplication by scalars. If these properties holds good, then we can say that H is a subspace of V. Null space. In the previous class, we have seen null space and column space. The null space of an m by n matrix A written as null A is the set of all solutions of the homogeneous equation Ax is equal to O. That is, null A is equal to set of X such that X belongs to Rn and Ax is equal to O, the null matrix. Null A is the set of all X belongs to Rn that are mapped into the zero vector of Rn. The null space of an m by n matrix A is subspace of Rn. These are the things which we have gone through in the previous class. And finally, the column space of a matrix. The column space of M by N matrix A is the set of all linear combinations of the columns of A. It is denoted by column space A. This is the symbol for that. And if A is equal to matrix of A1, A2 and so on AN, where A1, A2, AN are the columns of the matrix, then column space A is equal to span of A1, A2 and so on AN. This is the definition of column space of a matrix. So these are the things which we have gone through in the previous classes. With these concepts, let us discuss linear transformations in this class. A linear transformation T from a vector space V into a vector space W is a rule that assigns to each vector x in V a unique vector T of x in W such that the first rule is T of U plus V is equal to T of U plus T of V for all U V belongs to V, and T of Cu is equal to C times T of U for all U belongs to V and all scalars C. This is the definition of linear transformation. So linear transformation T is a function from one vector space V to another function, another vector space W. So it is a function between two vector spaces. One is named as V and second one is named as W. So it is a function with two rules. With these two rules. First rule is T of U plus V is equal to T of U plus T of V for all UV belongs to V. And the second rule is T of Cu is equal to C times T of U for all U belongs to V and all scalars C. So let us discuss in detail about these rules. T of U plus V is equal to T of U plus T of V. That means there will be no discount if they are taken at a time. For example, in a shop, you will buy a TV and a refrigerator. If the TV is 20,000 and refrigerator is 15,000, and if both are purchased at a time, if the shopkeeper gives you a rebate of 1,000, then you will get those at 34,000. So let us assume that T of U is the price of TV, U is TV, V is refrigerator, and T of U is price of TV, T of V is price of refrigerator. So T of U is 20,000, T of V is 15,000. But if both are taken together, the shopkeeper will give you for 34,000. In that case, T of U plus V is 34,000, which is not equal to 20,000 plus 15,000. So in that case, this rule fails. So in a linear transformation, there should not be such discounts. Even if you take both the TV and refrigerator together, the shopkeeper should not give you discount. Then only it will become a linear transformation. This is the first condition. Of course, that example need to be true for other properties also. Since V is a vector space, so your operation must satisfy all the conditions of a vector space. If that is satisfied, for this rule I am giving that example. Similarly, this is the second rule. T of Cu is equal to C times Tu. So if one TV is 20,000, if you purchase five TVs, that should be 1 lakh. No rebate should be given to you. In such a case, we can call it as linear transformation. So linear transformation is a function from one vector space to another vector space with these two properties. One is T of u plus v is equal to T of u plus T of v for all uv belongs to v, and T of Cu is equal to C times T of u for all u belongs to v and all scalars. Here we have to observe that u and v are elements of v. We are calling elements as vectors. So u and v are vectors of v, and T of u and T of v are vectors of w, the second vector space. So these will be T of u and T of v and T of u plus v, T of Cu. All these elements will be in W. So this is the definition of linear transformation. So let us discuss one more definition. The kernel of a linear transformation. Kernel is nothing but null space, which we have seen in the previous classes. The kernel or null space of a linear transformation T from V to W is the set of all u in V such that T of u is equal to 0 bar, the 0 vector in W. Here I have taken 0 bar to distinguish the 0 vector in V and 0 vector in W. So the kernel of a linear transformation is the set of some vectors in V which are mapped onto the 0 vector of W. It is denoted by kernel T. First three letters of kernel are written here. So we call it as kernel T. That is the mathematical definition, set notation of kernel is kernel T is equal to set of u belongs to V such that T of u is equal to 0 bar, the 0 vector of W. This is the set notation of kernel T. So we can observe that this is a subset of V, since all the elements are from V only. Those elements should satisfy another condition, that T of u is equal to O bar. So the vectors of V which are mapped onto the 0 vector of W forms the set of kernel T. So this is a geometrical representation. Let it be V. Kernel T will be a subset of V. This is W. T is the transformation from V to W. So This is the 0 vector, 0 bar. Here we get 0. So all these elements are mapped to 0 vector, 0 bar. So kernel T is the collection of all the vectors of V which are mapped onto the 0 vector of W. Here we have two 0 vectors, one in V, another in W. So to distinguish both the 0 vectors, we are calling O as 0 vector of V and O bar as 0 vector of W. So this is the kernel of a linear transformation. Let us move on to one more definition. The range of a linear transformation T from V to W. The range of a linear transformation T from V to W is the set of all vectors in W of the form T of x for some x belongs to V. It is denoted by R of T, or range of T. We call it as range of T. Simply write it as R of T. That is, range of T is equal to set of T of x such that x belongs to V. So clearly from the definition, range of T is a subset of W. Since each T of x will be in W. So its diagram will be like this. So these are all vectors in V. T is a mapping from V to W. So range of T is a collection of all such vectors which are from V. There may be some more vectors in W which are not from V. Those will not be a part of range of T. So range of T is the collection of all vectors of W which are mapped from P. So if you find an element in R of T, then you will find a corresponding vector x in V such that T of x is equal to that particular vector here. So for each vector in R of T, there will be a vector x in V such that T of x is equal to that. So this is the definition of range of T. Range of a linear transformation T. So if T is a matrix transformation, so transformation can be from any vector space to another vector space. So for a linear transformation, you need two vector spaces. So if T is a matrix transformation, say T of x is equal to Ax for some matrix A. So it is defined as T of x is equal to Ax. Then null space of A is the kernel of T. So null space will become kernel since it gives zero solutions. Null space is the space which is the solution set for the homogeneous equation, and column space of A is the range of T. All possible linear combinations of columns of matrix will be in column space. So in matrix form, null space of A or null A will be the kernel of T, and the column space of A is the range of T, that is R of T. So let us prove this statement. Kernel of a linear transformation T from V to W is a subspace of V. So kernel of a linear transformation is a subspace of V. Here it is given that T is a transformation from V to W. Here V and W are vector spaces. Linear transformation is possible only between vector spaces. So V is a vector space and W is a vector space. That means both the sets have those 10 properties which we have discussed earlier. So in both the vector spaces, there must be zero vectors. Let O be the zero vector of V and O bar is the zero vector of W. Then kernel of T is kernel T is equal to set of U belongs to V such that T of U is equal to 0 bar, the zero vector of W. This is the definition of kernel T. Then T of O is zero vector in V is equal to T of O plus O. Since O is the zero vector of V, so zero vector can be written as O plus O. O plus O is again O. That is why we can write T of O is equal to T of O plus O. So now it is in the form of T of U plus V. T of U plus V can be written as T of U plus T of V as per the definition of linear transformation T. So this is written as T of O plus T of O. Now both T of O and T of O both are in W. Since T is a linear transformation from V to W, T of O is in W. This will be in W. Second vector space. Since W is a vector space, there exists a vector minus T of O in W. So T of O is in W. So for each vector in W, there must be a negative vector such that U plus minus U is equal to O. Here, this is my vector. So there will be a negative minus T of O such that T of O plus minus of T of O is equal to zero vector. Zero vector is O bar here. So I can find a vector like this in the minus T of O. So by adding minus T of O on both sides to the above equation, T of O is equal to T of O plus T of O, we can get this one T of O plus minus of T of O, that is equal to, on the right hand side, T of O plus T of O plus minus T of O. This minus T of O is added on both sides. So T of O plus minus T of O is zero vector in W. So this is O bar. By associativity in W, I can exchange these brackets. Since we are in V, in W, all these elements are in W. W is a vector space in which associative law holds. That's why I can exchange these brackets. Now T of O plus minus T of O is again zero vector O bar. O bar is added to T of O, another vector in W. So O bar is equal to T of O plus O bar. So if a vector is added to zero vector, you will get the original vector itself, that is T of O. So finally we got T of O is equal to O bar. That means zero vector of V is mapped to zero vector of W through a linear transformation T. So this zero vector of V is mapped to zero vector of W. That's why I can say that O is in kernel T. So kernel T is the set of all such vectors which are mapped to O bar. Here O is also mapped to O bar. That's why O is in kernel T. So I am going to prove kernel T is a subspace of V. For that I have to prove three properties. First one is zero vector must be in kernel T. That is just proved now. The remaining two things are kernel T is closed under vector addition and it is closed under scalar multiplication. So first let us prove kernel T is closed under vector addition. Let UV belongs to kernel T. Let us take two elements in kernel T. Then T of U is equal to O bar and T of V is equal to O bar. This is the property of kernel T. If any element is in kernel T, then it must be mapped onto the zero vector of W. So these two elements U and V also must be mapped to zero vector of W, that is O bar. So T of U is equal to O bar and T of V is also O bar. So T of U plus V is equal to T of U plus T of V, since T is a linear transformation. T of U is equal to O bar, this one, since U is in kernel T, and T of V is also O bar, that is equal to O bar. O bar is the zero vector in W, so adding it twice will result you again zero vector O bar. So T of u plus v is equal to O bar. That implies u plus v is also mapping to O bar, the zero vector in W. So u plus v is also in kernel T. So we have taken that u and v belongs to kernel T. Finally, we got that u plus v belongs to kernel T. So whenever two elements are there in kernel T, the sum of those two elements is also in kernel T. So I can conclude that kernel T is closed under vector addition. Kernel T is closed under vector addition. So this is the second property of a subspace. Now let us move on to the third one. Let us prove kernel T is closed under scalar multiplication. Let C be any scalar and u belongs to kernel T. Let us take one element u in kernel T. Whenever u is in kernel T, the property is that T of u is equal to O bar. O bar is the zero vector of W. So T of Cu is equal to C times T of u. This is from the definition of linear transformation. The second property of linear transformation. This is the second property of the linear transformation. C of Tu. T of u is already 0 bar since u is in kernel T. So C times 0 bar is equal to 0 bar. This is one of the property of vector space W. Since these are all in W, W is a vector space. In a vector space, C times 0 vector is again 0 vector. So here we got that T of Cu is equal to 0 bar, the 0 vector. That implies Cu is also in kernel T. Cu belongs to kernel T. So Cu belongs to kernel T whenever u belongs to kernel T and C is a scalar. So I can say that kernel T is closed under scalar multiplication. So all the three properties of a subspace are proved here. First we prove that kernel T is a subset of V. Since all the elements of kernel T are in V, are taken from V only. Next we prove that 0 belongs to kernel T. Here 0 is 0 vector of V is in kernel T. Since it is being mapped to the 0 vector of W. Later we prove that kernel T is closed under vector addition. Now we prove that kernel T is closed under scalar multiplication. So all the properties of subspace are fulfilled. So now we can say that kernel T is a subspace of V. So this is the statement we require. Let us move on to one more statement which says that range of a linear transformation T from V to W is a subspace of W. So earlier we proved that kernel of T is a subspace of V. Now we are going to prove that range of a linear transformation is a subspace of W. So given that T is a linear transformation from V to W, so here V and W both are vector spaces, then only the linear transformation is possible. Let O be the zero vector of V and O bar is the zero vector of W, as we stated earlier. Then range of T is equal to, the symbol is R of T, that is equal to set of Tx such that X belongs to V. So from the definition of linear transformation T, T of X must be in W. So this is the collection of T of X's, that is from W. So it is clearly a subset of W. Since T is a linear transformation from V to W, T of X belongs to W for all X belongs to V. So range of T is contained in W, or it is a subset or equal to W. First, it is a subset of W. We show that. We show that range of T is a subset of W. So let us prove that again. T of O is equal to O bar, which you have shown earlier. So T of O is equal to T of O plus O, since O is the zero vector of V. That can be written as O plus O, T of O plus T of O, since T is a linear transformation. T of U plus V is equal to T of U plus T of V. Similarly, T of O plus O is equal to T of O plus T of O from the first property of linear transformation. Since T is linear transformation from V into W, T of O is in W. This must be in W. So all the game is happening in W. Since W is a vector space, there exists a minus T of O in W, such that T of O plus minus of T of O is equal to 0 bar, the zero vector. So since W is a vector space, all the 10 axioms hold in W. This is one of the axioms. For each vector U, there will be a negative minus U, such that U plus minus U is more. Similarly, here for T of O, there exists minus T of O, such that T of O plus minus T of O is equal to 0 vector of W. So by adding minus T of O on both sides to the above equation, T of O is equal to T of O plus T of O, we get. So I'm adding minus T of O on both sides. We'll get this equation. T of O plus minus T of O is equal to, already here it is T of O plus T of O plus, now we are adding minus T of O on this side also. So since we are in W, a vector space in which associative law holds, I can exchange the brackets and 0 bar T of O plus minus T of O is 0 bar, and here this is again another 0 bar, another O bar, we are calling it as O bar, which is a 0 vector in W. So this implies O bar is equal to T of O plus O bar. That implies O bar is equal to T of O. From the definition of vector space, from the definition of linear transformation, if we have O belongs to V, then T of O belongs to R of T for any vector. Here clearly, since V is a vector space, 0 vector O will be there. So O belongs to V implies T of O belongs to range of T. But here we have proved that T of O is equal to O bar. So T of O belongs to R of T, range of T implies O bar belongs to range of T. O bar belongs to range of T. That is what we have shown. So 0 vector will be in range of T. Next we prove that range of T is closed under vector addition. Let us take two elements in range of T. Elements in the range of T will be of the form T of X. So T of U, T of V belongs to range of T. If T of U, T of V belongs to range of T, then there must be two vectors in V, UV in V, such that their images are in range of T. So there will be two vectors U and V in capital V vector space. Since V is a vector space, there is some U plus V must be also in V. So U plus V belongs to V. U plus V belongs to V implies T of U plus V belongs to range of T. Whenever a vector is in V, its T image is in range of T. So U plus V belongs to V implies T of U plus V belongs to range of T. But T of U plus V is equal to T of U plus T of V. Since T is a linear transformation. Therefore, since it is in range of T, T of U plus V is in range of T, which is equivalent to T of U plus T of V, this is also in range of T. So T of U plus T of V belongs to range of T whenever T of U and T of V belongs to range of T. This is the closure property with respect to addition. So I can say that range of T is closed under vector addition. Finally, we are going to prove that range of T is closed under scalar multiplication. So let C be any scalar and T of U belongs to range of T. Let us take one element in range of T, that is T of U. Since all the elements in range of T will be of the form T of some element of V. So if T of u belongs to range of T, there must be some vector u in V. Since C is a scalar and u is a vector in V and V is a vector space, Cu is in V. By scalar multiplication, Cu is in V. That implies if Cu is in V, T of Cu is in range of T. So T of Cu is in range of T. But from the definition of a linear transformation by second property, T of Cu is equal to C times T of. This is the second property of the definition of linear transformation. So if T of Cu is in range of T, then this is also in range of T. So C times T of u belongs to range of T. So this is true whenever C is a scalar and T of u is range of T. So I can say that range of T is closed under scalar multiplication. So we have proved all the three properties of a subspace. First, we proved that range of T is a subset of W. Later, we proved that zero vector is in range of T, zero bar in range of T. And later, we proved that range of T is closed under vector addition. Now we proved that range of T is closed under scalar multiplication. So from all these properties, we can conclude that range of T is a subspace of W. So let us see some of the applications of kernel T and range of T. In applications, a subspace usually arises as either kernel or the range of an appropriate linear transformation. So in many of the problems, those problems will be finally modified into problems on subspaces where those subspaces will become either kernel or the range of linear transformation. For example, the set of all solutions of a homogeneous linear differential equation turns out to be the kernel of a linear transformation. So, if you take a system of homogeneous linear differential equation, that system will become solving that system will become finding a kernel of a linear transformation. So if you are able to find a kernel of linear transformation, you will be able to find the solutions for the homogeneous linear differential equation.